Okay, for the next hour I want to talk about molten slags, molten oxide, silicates, borates, which I started last time. I'm going to use files 49 and also 41. I think I think many of you are actually working on molten oxide databases or something, so this should be So a quick review. Well, actually, I was going to say last time I talked about molten salt systems such as KCl, MgCl2, or let's call them AX, MX2, things like that, where you have the tendency here is to form your MX4 complex anions. I guess I wasn't clear because I was asked afterwards. The trends, in other words, is the tendency to form complex ions stronger or weaker depending on the values of what A, X, and M are. Okay, so higher, so is A plus, this is your alkali, lithium, sodium, potassium, rubidium, cesium. As A plus becomes bigger, okay, complex becomes more. Maybe we got that wrong. Remember, as you go down the series, lithium chloride, magnesium chloride was very uncomplex. As you go down to cesium chloride, magnesium chloride, you get a much stronger complex. So as the A plus becomes bigger, the complexing becomes stronger. Okay. As M2 plus smaller, the complexing becomes stronger. All right, if you've got a little tiny M2 plus here, it pulls the chlorines in very tightly around it and forms a very strong complex. So if you've got something small like beryllium, you get a really strong complex. If you got something big like lead in the center, it forms a weak complex. And the fluorine ion, as X minus is smaller, the complexing is more for the same reason. If you got small anions, fluorine, around your central ion, they tend to form strong complexes. If you've got big anions like iodine, they tend to form weaker complexes. So your strongest complex would be something like the strongest then in this, if say you were dealing, say the X are halides, the A's are alkalis, and the M's are alkaline earths, and your strongest complexing would be cesium fluoride, beryllium fluoride. And your weakest would be something like lithium iodide, barium iodide. Okay, so I went through the molten oxides. So very quickly I talked about basic oxides, which are ionic oxides, which are just like molten salts, highly fluid, etc., etc. Two sublattices. Then you have your network formers, which tend to form covalent bonds with bridging oxygens between your metal ions, tetrahedral, trigonal, or complex things. This is your structure of silica. Every silica is at the center of a tetrahedron. It's not planar, these are three dimensions. The four oxygens are very strongly directed towards the centers, towards the corners of a tetrahedron. The angles here are the tetrahedral angle, 103 plus something degrees, and that can't change because otherwise the energy goes way, way up. So it's a very rigid network. These are called your oxygen bridges, and this is a very highly viscous, non-ionic, gooey material, okay, with a network. As you adding a basic oxide, it modifies the network because the oxygen ion that you add from your, Jesus, I hate these things. Why does it not work for me? This is the third one I've only. Well, I can use cursor, I suppose. As you add the oxygen ion, this is your oxygen bridge. This is an oxygen bridge. This is your oxygen ion, which came from the calcium oxide, and that's forming a broken bridge. The broken bridge is a center of negative charge. There's a couple of minuses on here, and so there's an attraction here, so the tendency is for the cations to remain next to the broken bridge. If you add Na2O, then of course you get a broken bridge, but then you need two sodium ions to supply one oxygen ion, and so you probably have something like that. We've been through this before, so I'm going quickly. So the composition, as you go across from, say, calcium oxide to silica, the structure of the melt would be something like over on this side, which we call the basic region. We would have mainly calcium ions, oxygen ions, and orthosilicate ions, looking something like that. These are SiO4 ions, are called orthosilicates. At Ca2SiO4 you have mainly calcium and orthosilicate ions, and then as you get further on, well, starting at this side now, you've got starting at the other side, you have the previous slide, you have your network, and as you move across this way you start to break up the network like we did here. So every time you add a calcium oxide you snip one of these bridges. Okay. And you can sort of imagine that this structure was built up with little sticks and balls like Tinker Toys. Like you have little balls and you have 4 oxygens around it, and you started to cut these little bridges one at a time. At a certain point the whole thing would collapse, and that's the point where the viscosity starts to drop like really fast. Okay, and then you're going to get big chunks, and then you're breaking up the chunks into smaller chunks, and you move back to the point where if you break them up entirely you have only SiO4s, orthosilicates. Okay, or you can start from the other direction, and let's say we're over here, and now this is the limit to which you could get with Ca2SiO4, just like the potassium magnesium that I was saying. And as you go a little bit further over on this side, you cannot have only SiO4s because you don't have enough oxygen. So now you can start to treat the thing as dimers. So you can imagine you have your SiO4s, but they share an oxygen, and that's a dimer, Si2O7. And you can get trimers and tetramers and so on. But after a while that starts to get silly because you got long chains, and you have branched chains, and then you can start to get rings, and then the rings coalesce into big chunks, and you end up with the 2 sides sort of kind of like this. So over here it's very fluid. It's about the fluidity of water, like molten salts. When you get over here your viscosity is about 20 orders of magnitude higher. Somewhere in here the viscosity goes way up. Ionic conductivity goes way down because you no longer have ions which can carry. Here you have ions which can carry the charge. Over here you don't. So that's how the thing goes. Now, how do you model this thing? Some of the first attempts at modeling were really to consider these discrete ions, Si2O7, Si3, and so on, which would take you, well, over on this end, as we've already shown, a very simple model is just simply treating it as the complex ions. You can go a little bit further by treating it as having dimers and trimers, but then the dimers and trimers can't really occupy just one site. I mean, if you have an Si4 or whatever, that's a big anion, that can't occupy the same site as a little oxygen. So you can sort of imagine there are 4 sites that it can move itself around. You have, these are where you put the silicons, and you would have a trimer like this, but I mean it could also go this way or it could go that way. And way back in the 50s, a guy called Masson, who was a guy from Nova Scotia, had Masson's model, which was kind of a way of mixing these linear chains along with monomers, but it really wasn't terribly successful, but it was the first attempt at it. I won't go into Masson's model. We talked about there's good experimental evidence for this from the magnetic resonance and Raman spectroscopy and so on, which I've already talked about. How do we treat the thermodynamic properties as functions of composition? Well, I said we can treat it by in the very basic region, we can treat it by the discrete SiO4 ions, but we actually treat it as first nearest neighbors. Silicon form 2, magnesium, silicon, second nearest neighbors. So we're talking about the metals and the silicons, the calciums and the silicons mixing on the cation sites, and it's exactly the same thing as as we were talking about earlier with Elmira, your question. You can consider this to be a discrete ion, or you consider that to be a silicon-calcium preferential second nearest neighbor. This thing's going to be surrounded by calciums, and so as long as you don't have very many silicons, that will be a rough model that this thing is equivalent to a complex SiO4 ion. Okay, but then if you start to get past Ca2SiO4, your complexes would have to share at least an oxygen, then you start getting dimers, and you start getting trimers. And as you get even further, probably the best way to treat it is simply to consider the second nearest neighbor and do it with the 1 sublattice quasi-chemical model, which is what we do. Enthalpy of mixing looks like you would expect. You have a very strong minimum, around 33%. which is the M2SiO4 composition, because that's where you have the strongest complex, the strongest at the 33% composition. That's where you have the calcium and silicon secondary as neighbors, or you have the complete Ca2SiO4 complexing. It's the same order as I did, say, with the chlorides, lithium chloride, magnesium chloride going down, sodium, potassium, rubidium. It's the same thing as you go down the periodic table with the magnesium, calcium, strontium, barium, you get stronger. As the cation barium is bigger than magnesium, you tend to have stronger complexing, a stronger tendency to break up, or stronger or Ceramus would say barium is a better network modifier than magnesium. It has a stronger tendency to break up the network, makes it more ionic. Entropies follow the same trend. The barium clearly has the lowest entropy, the magnesium has the next lowest entropy. Your Gibbs energy is extremely negative, with an extremely negative peak at 33%, minus 65 kilojoules. Remember, your ideal entropy is going to be somewhere up here. Ideal Gibbs energy of mixing is up here somewhere, which is huge. This is almost a perfect straight line. Over on this side, you have a very small blip, which gives rise to the miscibility gap. Activities, of course, drop like crazy. The activity of calcium oxide, which is the intercept over here, stays almost constant and then just drops down to an extremely small value. Okay, so you tend to have that type of activity curve. And over here you have a miscibility gap, which is due to the fact that here you have this more or less ionic liquid, and over here you have this very covalent network liquid, and they just don't really want to mix. But now, they said this does not mean that you have positive deviations from radiality. People say, oh, miscibility gap always means positive deviations. Well, no. Here's your miscibility gap. If you're on this scale, you can't even see it. Remember, there's a little hump like this. Okay, the ideal mixing is like this, like the -5 or something. Okay, so this is always more negative. Okay, even if you did not have demixing, even if you were in the middle of the miscibility gap, you just had one metastable liquid, that would still be a much more negative Gibbs energy than your ideal solution. Okay, but there is a slight hump indicating you can get an even lower, even a slightly lower Gibbs energy if you will separate into the two phases. But even if you didn't separate into the two phases and you had a metastable liquid here, that would still be far more stable than an ideal solution, because this is an extremely negative. The Gibbs energy of this is extraordinarily negative, -100. Sodium silica is the same. You don't actually see the miscibility gap, but you see it manifested by this S-shaped liquidus. So if you suppress the formation of silica, which is almost impossible not to do because it doesn't want to crystallize, you get a miscibility gap down here between the two supercooled liquid phases. Now, before I go on to this, I'm going to go to the other slide, the other thing, number 41. Why is it called South Africa? That's because we gave a talk in South Africa. And we'll skip the first part, which is on molten salts. And we'll go directly to silicate slags. This is just the same thing, but just kind of present it from a little bit different area. Here's your silica, calcium, magnesia system. Look at this red trapezoid here. This is the basic region. This is from CaO to Ca2SiO4 and MgO to Mg2SiO4. So in this region you have mainly, okay, this region is roughly modeled as calcium, magnesium on this lattice, and on the other lattice you'd have oxygen ions and SiO4 ions. Okay. That's called your basic region. So slags in the basic region are very fluid. All right, this is quite normal for this type of thing. This is your liquidus projection. You notice that along this line here, the liquidus lines are quite widely spaced. They're more narrowly spaced as you go along here. This is a quasi-reciprocal system. Okay, this is a reciprocal system: calcium, magnesium, oxygen, orthosilicate. Okay, so here's CaO, this is MgO, this is CaSiO4, and this is MgSiO4. These are your four end members of your reciprocal system. Now, it's not exactly reciprocal because Ca2SiO4 isn't exactly calcium SiO4, You have some dimers, trimers already, and magnesium even less, more so. Okay, so this is not exactly Mg2 plus SiO4. This is more complicated. You have some tendency to dimerization already, but to first approximation, this is a reciprocal salt system, just like sodium chloride, potassium fluoride. I mean, you have two cations and two anions. And this is obviously the stable pair, which means that the exchange reaction, and you can get this just from looking at the Gibbs energies of the pure materials, liquid, CaO plus Mg2SiO4 gives you MgO plus Ca2SiO4. The Gibbs energy for that reaction is, this being the stable pair, that's negative. Okay, so along the stable pair, you always get your positive deviations. Magnesium likes to be next to oxygen. Calcium likes to be next to silicon. The calcium-silicon, second nearest neighbors, if you like, are stronger than the magnesium-silicon, second nearest neighbor. Okay, because calcium is bigger than magnesium. Remember, as you go down the periodic table, you get stronger complexes. Stronger tendency to form complexes as this ion here gets bigger. Okay, so these complexes are more stable than these complexes, if you like, or the calcium prefers calcium silicon, calcium orthosilicate, second nearest neighbors, are preferred over magnesium orthosilicate neighbors. So if you tried to mix MgO and calcium silicate, you force the calcium to be next to the oxygen and the magnesium to be next to the silicate, which it doesn't like. It's exactly the same thing as it's a molten salt solution. All right. So there's your exchange reaction, and the delta G exchange is negative, which is what I just said, so there's a tendency to immiscibility along the MgO-Ca2SiO4. Join, as is evident from the widely spaced isotherms. Now, in an associate model, we talked back a long time ago about associate models. You know my opinion of associate models. We're assuming that MgO and silica form an associate. This is not ionic. We're talking about an Mg2SiO4 molecule. Okay, and people have treated these things, and as I said, in the binary systems, you can treat them quite nicely with an associate model. But remember, the problem with an associate model, when we were going back to molten salts, is the associate model. Then, if you treat these as associates, this is a if you like, this is a Ca2SiO4 molecule, and that's a CaO molecule. You can treat the binary systems fine, but when you go to the ternary, you're going to get an ideal solution across here. You're not going to predict the positive deviation, which are like a major thing. Okay, so you get really crummy predictions in the ternary systems. I don't have to go through that again. So with the model parameter for this formation of complexes, one can reproduce the Gibbs energy of the binary reasonably well. Okay, but since delta G exchange is negative, the solution along the MgO calcium silicate joint is modeled as consisting mainly of You still have the exchange reaction. Even if you have associates, you're modeling these now as molecules. Your delta G exchange is negative, so along the diagonal between this and this reaction is strongly shifted to the right, so you do have these and these. It predicts correctly that the calcium silicate tend together and the MgO tend together, but it treats them as an ideal mixture, so you don't get the tendency to miscibility. Okay, you may have heard of the Ionic liquid model. This is a new thing. You probably want to listen to this. I don't like the Ionic liquid model, but it doesn't work too badly. This is also called the Stockholm model. This is the model that is used by thermocalc. It's the model that is used by all the, not just for slags, but it's used for lots of liquids in which you have short range order. It's kind of a this Ionic liquid model is basically in the thermocalc, SGT, whatever software, they cannot take account of short range order. They don't have the Quasichemical Model. So they try to and they know that the associate model doesn't work that well either, so they try to do kind of I won't use the word half-assed way of doing it. Anyway, in equilibrium, you have calcium and magnesium are randomly distributed on the cationic sublattice. Oxygen ions, orthosilicates, and neutral silica species, because they want to go beyond the orthosilicate. They want to go all the way to the top. And neutral silica species are randomly distributed on the anionic sublattice. So right away, this is a very artificial model. So they're mixing So we can see in the basic region, having this and this on the cationic sites and this on the anionic sites is pretty close. By having SiO2 species, though, you don't have SiO2 molecules also going on the anionic sublattice. This is really artificial. An equilibrium is then established between the neutral SiO2 species, the oxygen ions. So this is a equilibrium that's going on in this model on the anionic sublattice, and the delta G for this is negative. So this is actually quite similar to this bond-breaking reaction. O0 plus O2 minus produces 2, and this is your O0. But, I mean, the way they're distributing these is just not right. You don't have, I mean, this model actually has, on one sublattice, it has oxygen ions, SiO4 ions, and SiO2 molecule. So it doesn't explicitly take into account the network. Pure silica is considered to consist of SiO2 molecules on a single lattice. I'm not going to go into details with this model because I don't think you're going to use it to. Okay, and the basic melts then, it's the same thing though as here. These are randomly distributed. The tendency to immiscibility is predicted, but it's overestimated because the short-range ordering is neglected. You remember back when we had, if we used the Bragg-Williams approach with the 2 sublattice model, you ended up overestimating it. Okay, so they're basically in the basic region down here, they're using it's a Bragg-Williams model to all intents and purposes. Okay, it's a Bragg-Williams model. They're doing it ionically, the magnesium and calcium on one lattice, the oxygen and the orthosilicates on the other, but they're using a Bragg-Williams model. So what you get along here is you get too big a gap. In fact, you actually produce a miscibility gap in this particular system. If you just use the parameters from the binary system, you can't predict the ternary. You overdo it. Remember, the associate model gives you no miscibility, no positive deviations. The Bragg-Williams gives you too much. Okay. So they're randomly distributed, so the tendency to miscibility is predicted, but it's overestimated because you neglect the short-range ordering. The effect of short-range ordering, then, they put in this artificial. They put in the big L, the big lambda term. This was your short-range order, Taylor expansion, the product of the formal fractions times a constant, which they. If you remember this constant now to a first approximation should be delta Gx change squared over 2ZRT. If they put that in, it makes it better, but it doesn't really give you a quantitative thing, so you really have to treat this as an adjustable ternary parameter, which you adjust to fit the ternary system. Very acid solutions, so these are at the top part of the triangle, are treated as mixtures. At the top part of the triangle now, if you're up here, according to their model, you'll have very few oxygen ions, O minus minus. So over this side, you'll have magnesium and calcium on the cation lattice, and you'll have SiO4 2 minus and SiO2 neutral species on the other sublattice, which permits you to extend the treatment at least up to silica, but it's certainly not a very realistic sort of model. So very acid solutions are modeled as mixtures of neutral SiO2 molecules of SiO4. The model, however, has been used with success to develop a large database for multi-component slags by the group in Stockholm. But I was being kind of generous here. This was a public conference. Okay, however, I'm prejudiced. Okay, the Pelton-Blander model is the quasi-chemical model between pairs, which this model here is called the Toop model. It's nothing to do with the Toop model we talked about before. Toop was at University of British Columbia, actually. He did quite a few things, but he came up with one of the early models for the slags, in which he simply mixed the oxygen, neutral oxygens, the bridges, the oxygen ions, and the broken bridges on the sites, and this does give you a reasonable picture. I mean, it's to a first understanding of the system. So in basic melts, you have mainly these pairs because delta G is negative. That is, most silicon atoms have. Well, we talked about this. However, the clustering, the quasi-chemical exchange model then gives you the short-range order, so you get the proper positive deviations along the main diagram. There's a third model which you'll come across. It's called the cell model, or the Kapur-Froberg-Gay-Weltringer model, called the Gay model, the Froberg model, the Kapur-Froberg model. It's also called the IRSID model, IRSID, which is the Steel Research Center in France, and they've developed a database using this, which tends to be in the thermodata system. And the way they've done it is they've talked about the system is considered, slag is considered to consist of cells which mix ideally with equilibrium among the cells. So you have a magnesium, oxygen, magnesium cell. You have a silicon, oxygen, silicon cell, and you have magnesium, silicon, oxygen cells, and you'd have the same thing with calcium, 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 magnesium. Okay, and these cells mix randomly, and the delta G is negative for this reaction. And as you can see, it's very close to the Quasichemical model. This is basically the Quasichemical equation. What's different is the entropy expression is somewhat different. They don't use the Quasichemical entropy expression, they're using an expression for actually mixing the cells, but it's very close. Okay, so basically the cell model, it's quite similar, I would say even very similar to the modified Quasichemical model. You have the heat of mixing, enthalpy of mixing is due to these things, and your entropy of mixing, it's somewhat different than the Quasichemical model, but it's pretty close to the same sort of idea. It accounts for the ionic nature of the slags, and it accounts for the short-range ordering, because it's this Quasichemical model, so you do get the short-range ordering done pretty correctly as well. And it has been applied with success to develop databases for multi-component systems. And if you see people talking about the IRSID database, that's the database, that's the model they use. Now there has been some attempt in Thermocalc and SGT to also use the IRSID database. The problems with this are, A, I've never been able to actually find a paper which gave exactly all the explicit equations for the thing, but I'm pretty close to it. Okay. The other thing is, I would think that really, if they really applied this model completely as we apply the Quasichemical model, I would have to say that I think the database they would develop would be of about the same quality as ours. They just have not had the personnel to put the effort into building up the great big database that we have. So the database is not as extensive because of the lack of just the lack of people over the years developing the database. Not because the model, I think, is terribly bad. I think the model is pretty good, and it's awfully close to the Quasichemical model. We have not programmed it because I couldn't see why we... you can't mix these two models. We can't take theirs and put it into our databases, but they're still quite close. Okay, you can find some references to these. I can give you references if you want. And that's the IRSID model. But their database is not as extensive as ours. And I don't think they've taken quite the care to getting as close to the experimental, to try to do the optimizations as closely as we do by putting in the terms and so on, but it's more a matter of lack of personnel and time than a lack of a good model. The ionic liquid model, however, I don't think is good. And I don't think there's too much. Okay, so that was the number 41. So that's just kind of looking at the whole thing from a different standpoint. Let's go back to the 49. So now we're back to okay, this is back to the number 49. We just talked about that. Okay, so now I'm going to go on with this. Okay, so that's the structure of silicate slags. And germanium oxide slags as well would be the same thing. Okay, so you have your basic oxides, the alkaline oxides, the alkaline earth oxides, FeO, MgO, PbO on it, and you have your silicon germanium. Now you have Al2O3, which is called amphoteric. T-E-R, amphoteric, Al2O3. That means people say it can be acid or base. And exactly what does that mean? Okay, if you take, this is your Al2O3 SiO2 phase diagram. And you can see in that diagram you have actually somewhat positive deviations from ideality. But remember, if you mix a basic oxide, if you mix CaO and SiO2 or Na2O and SiO2, you get very negative liquiduses that go way, way down. A very negative Gibbs energy mixing. Here you clearly don't have a negative Gibbs energy mixing. The aluminum is not really wanting to mix with the silica. They're not really wanting to mix terribly bad. So let's look into this. This is a corner of the sodium silica alumina diagram. Here's silica, down here you got sodium, and here you got alumina. These are the Liquidus curves. The diagram I just showed you was along here. Silica with alumina. As you take silica and you add alumina to it, they don't want to mix terribly much. They're quite a high Liquidus. But if you, at the same time, you start here and you start to add some sodium oxide, then look how fast these Liquidus curves, these are every 100 degrees, no, 50 degrees, 100 degrees. This just comes down vertically. In other words, it becomes extremely stable. If the Liquidus goes down, it means the liquid is being hugely stabilized by adding sodium and alumina simultaneously. So why does adding sodium oxide does not terribly much stabilize it. Adding alumina gives you positive deviations. Adding sodium oxide, okay, we've seen the sodium diagram. This does bring it down quite quickly because it's the acid base. But nothing works better than you put the two of them together. And this is due to what is known as the charge compensation effect. And this is the following. This is supposed to be your silicate network over here. So these little red dingies are silicon, and the white and the orangey things are oxygen. It's really SiO4, but you don't have it out here. So this is your network. This is your silicon with the oxygen. So the silicon, we could call it a silicon 4+. This is its valence. If you try to put an aluminum onto that site, the charge is unbalanced. If you replace a silicon by an aluminum 3+, then the charge is unbalanced here. So it doesn't want to go in. The aluminum can't go into the network. Aluminum can't replace a silicon in the network if you just add aluminum oxide. But if you add aluminum oxide and sodium oxide in equal amounts, then the aluminum goes onto the lattice into the network site, and the sodium goes right beside it to balance the charge off. So the aluminum and the sodium together form 4+. So this is a charge compensation. So basically what's happening is the aluminum, it's not going in as a basic oxide, it's going into the network, replacing the silicon, but it can only replace the silicon if its charge is compensated by a sodium. And now it goes in very, very strongly. So if you add sodium and aluminum in equal amounts, you add NaAlO4 essentially, okay, you get a very, very negative effect because the aluminum can form a very strong affair here, and this is called the charge compensation effect, which definitely cannot be predicted from the binary data. This is a true ternary effect. Okay, there's no way that you can predict the charge compensation effect from the 3 binary systems. You optimize the 3 binaries, it gives you no information on this at all. This is a true ternary effect. Similarly, you could add calcium oxide to break the bridges to compensate it, but now you've got a problem with the calcium oxide. This is calcium now, which instead of the sodium, the calcium is 2 charged. So if you just add calcium and aluminum oxide, you would get overcompensated. Now you would have calcium 2+. So you really got to have a calcium 2+ with 2 aluminum. So your calcium plus 2 aluminums would come together. So 2 aluminums would have to be close together, 2 aluminum 3+s and a calcium 2+ in order to get a total of 8+. And this is less likely just on probability. Therefore, divalent ions like calcium have less of a charge compensation effect than monovalent ions like sodium. But this is like a huge effect. It dominates the phase diagram. So you see what's happening here. This goes down from 1900 degrees down to 1000 degrees over here. Okay. This line here goes down to NaAl. Do I have another one? The bottom of this anyway comes out, if you project this line down all the way to the sodium alumina base, you're going to find that you have silica, Al2O3, here you have Na2O, and here you have NaAlO2. NaAlO2 is like SiO2 basically. The NaAl replaces the silicon. The aluminum on the lattice site, the sodium sitting next to it. Okay, so this is your maximum charge compensation line, which is this line here. This is another compound that's halfway in between. Okay, so this side just drops down really steeply. In the last little bit here, you can see the 100-degree isotherms are right on top of each other. And then over on this side, things are quite normal. So this basically divides the system into two subsystems. You basically have this subsystem. You have a subsystem over here. This is actually going along this line. Albite is on this line here. Okay, so I haven't gone all the way because there's no data down to here, but there's data along that line. That's NaAl. Is that right? Am I right there? How many do I have the right number of silicons? Yeah. I have NaAlO2 and Si3O6, which is 2 times SiO2. So this is albites on that line. Okay, so this is the liquidus line from here to here, going down to here. And this is the important thing, is over here. This is silica over here. So this is the liquidus curve as you go along here. And this is almost an ideal solution. If you treat this as an ideal solution of NaAlO2 and SiO2, you almost perfectly reproduce this curve, because the NaAls are mixing with the silicons. It's almost an ideal solution. There's your calciosilicon. Remember I said the calcium oxide is a much less of a, okay, so again you can see here, there's calcium. If that were sodium, this would be coming down really, really fast. It just isn't here. The charge compensation factor is much, much less when you have a divalent, because it can't, you need 2 calciums to compensate the charge. I think the best evidence, there's also NMR evidence, and you can do molecular dynamics, and you always end up with this Al sodium pairs replacing it. But I mean, the simplest evidence is this is an ideal liquid. You see, just NaAl is replacing silicon. So, charge compensation effect is very important. How you model it is not quite so easy by any means. In fact, the sodium aluminosilica is about the most difficult phase diagram we've ever modeled. You could talk to Inho about this. You might say, okay, why don't we just treat it by the quasichemical model, and we just say that this is a really strong, this is just an aluminum-sodium second nearest neighbor pair. We just make the second nearest pair as aluminum-sodium very, very strong. It doesn't work. These really have to be treated as associates. I consider NaAl, that's an associate. If you treat it as an associate, it works. If you don't treat it as an associate, no matter how strong you make that thing, you'll end up with the wrong slope over here. Your limiting slope will always be, the sodium and aluminum will always, unless you make it like infinitely strong, your sodium and aluminum always start to dissociate as you near the silica, so you end up with a steeper slope here, and it comes around like this. You can't do it. The minute you treat the sodium aluminum as just a complex, NaAl is a complex cation, everything just works beautifully. So that's your charge compensation effect. That being said, to try to treat this quantitatively, along with the fact that in this solution here, you don't just have a complicated liquid, you have very complicated solid solutions with all sorts of sublattices and stuff. Okay, trying to put in the alkali, so here you've got a silica, you've got an alkali, a basic oxide, and this amphoteric oxide. Okay, this is a real modeling challenge, but we have, I think, come up with something. Or there's no way you can possibly fit this if you don't somehow explicitly take into account the charge compensation effect. Borates, B2O3, which are important in glasses and things. They're very low melting oxides. Borates are like silica, they have a network. But the boron is a group 3 element, so you have also, their network is not simple. SiO2 is a simple face-centered cubic SiO4 network. Borates can drive you crazy. You have the boroxyl group, which is boron with 3 nearest neighbors. Oxygen, and kind of like a puckered plane. The boron's here, the 3 oxygens are down here. There's a lone pair of electrons up here. But the boron can also find itself in tetrahedral coordination, and it can form tetraborate groups mixed up with triborate groups. As you start to add if you add sodium oxide and calcium oxide to it, then you can start to distinguish all sorts of ways that you can put the 3s and 4 things around it. You can also imagine then if you try to mix boron with silicon, then the silicon can occupy the tetraborate, the tetrahedrally coordinated sites, and the actual structure becomes extraordinarily complicated. But it still is a network structure, it just ain't a simple network structure. If you take the sodium boron oxide system, you can see that you got very, very strong complexing on this side. This just goes down like crazy, down to 400 degrees here, and then 15%. But you have all sorts of compounds which kind of mask what's going on in the liquid state, because the solid compounds are also very, very strong. But we can look at the enthalpy of mixing. This is the enthalpy of mixing of sodium oxide and boron oxide. This was the minimum at the 25% composition. This is like minus 75 kilojoules here, which is even worse than the silicates, extraordinarily negative. This is basically Na3 plus, BO3 3 minus. Okay, so up to here you have complex ions, BO3 3 minus, just like the SiO4s. But then as you start to move across here, then you start to get all these tetraborate crazy complexes, and the tetraborate complex is over here, the NaBO2, which is quite a bit like this NaAlO2. If you go across the diagram from NaBO2 to SiO2, you tend to get pretty well an ideal solution. So the NaBO2 is probably quite close to an SiO4 composition. The Na and B are charge compensated, and this forms like a silicate network, but not exactly. Okay, so this is very much like, this is basically like SiO2. The NaB are charge compensated, just like NaAl. Okay, and then you start to get all these crazy things on that side over here, and we've tried to model this. Somehow it's driving certainly crazy. But okay, over here at least, the region which is practically of no interest, you have sodium ions and triborate ions, which are quite simple. This is more or less like silica, I think, tetrahedrally coordinated stuff, and then you get all sorts of things as you go over towards the over here. The enthalpy of mixing, though, is the same thing, and you see the network modifiers, like as you go down the series, tend to be more and more important. Your barium oxide is your strongest network modifier. It has minus 110 kilojoules, which is a huge, huge entropy of mixing, enthalpy of mixing. And the entropy same sort of thing. The boron silica phase diagram, here you're mixing two lattice formers. Here you're mixing silica, which is tetrahedral lattice, and here you're mixing it with the boron, which is a complex lattice. And the tendency, of course, is to get they mix somewhat positive deviations. You also got this huge difference in temperature. The melting point of silica is about 16 something, 17 something. The melting point of boron oxide is 450. Enthalpy mixing slightly positive activities, but they're pretty close to me. That's pretty close to an ideal solution, actually. BO1. If you treat it as BO1.5 and SiO2, you're kind of close to that, pretty close to an ideal solution. Okay, that actually I said alumina, silica, sodium was the worst. No, this is the worst. Silica, boron, sodium oxide system. I won't even talk about that. In that system you have, this is silica, boron, oxide, sodium. Just to show you about a modeling challenge. This is a reciprocal miscibility gap. Going from SiO2 up to the tetraborate composition. And by the reciprocal miscibility gap, I mean like when you cross the reciprocal system. Okay, here you have a very strong, you might expect, however, that you would get the reciprocal miscibility gap between silica and this composition here. which is the very, very negative one. If you don't, you get it between the silicon and the tetraborate composition. So you got a, definitely you got a, this is a very strong complex, the tetraborate, with the silica, and there's your, okay. On the same cup though, remember in silica, the sodium's up here, and SiO2, this is down around 500 degrees, so this is a metastable liquid in the glass region. You have this binary miscibility gap here, which collides with this miscibility gap. So here you have a mixed, you have two miscibility gaps coming together. This is sodium oxide and silica have a metastable liquid-liquid miscibility gap, which collides with this reciprocal miscibility gap due to the exchange reaction being negative. And in the base, the silica boron system, if you take the silicon boron system to that low temperature, over here, if you suppress the formation of silica, you get a miscibility gap down here too. Okay, so you have the three miscibility gaps coming together. You have this binary miscibility gap, you have a binary miscibility gap down here, all colliding with this miscibility gap. Plus the experimental data are not very accurate, and trying to model this has been lots of fun. This was along, I said this was from the NaBO2 to the SiO2 section across the ternary diagram, and this is very much like this system. This is almost an ideal solution on both sides. Not quite, but pretty close to it. Okay, showing that this is pretty much NiBs are mixed, sodium Bs are mixing with silicons on simple charge compensation. Okay. But this is about the only simple cross-section in the entire system. Won't go into that. We talked about that. And we talked about that. I don't think there's anything else here. I was trying to self-fixate. Okay, so now you know all about silicate and borate aluminum oxide slags. Then there was the other one, was the sulfide capacities. I already talked about that. If you dissolve sulfur as sulfide ions in these slags, you can use the modified quasi-chemical model in the what do you call it? Four things. Quadruplet. In the quadruplet approximation, putting oxygen and sulfur on one lattice and putting the silicon, whatever the alkalis, on the other lattice. Okay, and that was in, if you want to look back at that, that's in file number 48. Okay, so that certainly is not everything you could learn about slags, but that gives you an idea. We use the quasi-chemical one sublattice model here, except when we put in sulfide ion, and then that goes on the sublattice along with the oxygen, except sulfur, of course, does not form a network. Sulfur is always S2-, even when you're in pure silica. The sulfur doesn't form bridges between silicons. It remains ionic, okay, which of course makes life more complicated when you're over at that corner. But Yunbei Kang, who was with us here for some years, has done a really good modeling job on the sulfide and oxide and silicate slags, all the way up to this pure sulfide side, actually. So, anyway, handout number 48 is the paper we wrote on it, and I think you, now being experts in solution chemistry, could read that and more or less understand what he'd done. All right. Want to take a break and talk about the exam? Or do you want to just talk about the exam and forget the break? I'll give you the exam and you can look over the exam and think about it. Okay, it worked out very well. The class average was out of 20, 15.86. And I have written on each of the papers here, I've given you your mark in red is the mark you have for this exam, and then underneath I've given you a final grade, A, B, C, D, E grade, which is the final grade for the two quizzes together. Okay, I just kind of took the average of the two quizzes. I arbitrarily decide what's an A, B, or a B minus or whatever. Okay, and I've given you the final grade. This is the final grade you will get on the course if you didn't write the final exam. Okay, I think you should be reasonably happy with these. Okay, I also tried to mark it. I'll be marking what the meaning of an A and a B and a B plus is a little bit different at Polytechnique than it is at McGill. We've run into some trouble with that before, because I gave a student a B minus or a C plus here from McGill taking this course, and he said I failed. Okay, so I've tried to take into account the norm, the standards of McGill in this thing. Also here we have A pluses, McGill doesn't have A pluses, so I didn't put it in A pluses. Okay, Mr. Panda, Elmira, Mr. Kim, Dimitri, Silva, Trilogy, and Pilar. Okay. So you can look that over. We'll go over the mark. We'll go over the thing afterwards, the actual answers. I was quite happy. It said it's 15.86 was the average. Okay, you may, if you wish, think this over. That's the final mark you got on there, your letter grade that you will get if you don't do the final exam. You may choose if you wish to. Those who have A's would certainly have no point in doing the final exam. Those who have less than A might consider doing the final exam if you want to increase your grade, but I do warn you that if you take the final exam and mess it up, you could get a lower grade. Okay, I'm not going to take the attitude that it's either, you know, if you get a lower grade, I'll just give you this one. No, if you screw up the final exam, you get a lower grade. I would then strongly recommend that you don't do the final exam, because I think the grades here are pretty good and probably reflect what you would get on the final exam anyway. But you can think about it. I promise that you can have a final exam on December 7th if you wish, and those who want to take one can, but be warned that it's going to be a final exam on the whole course. And okay, so turn this thing off.